Okay, so we're going to have a look at the very first lesson in your acid-base equilibrium or acid-base theory notes. This is to allow us to calculate the pH of two things. We're going to look at a strong acid and we're going to look at a strong alkali. We're also going to take the pH, I suppose I should say, we're going to take, in both cases, we're also going to be able to take the pH and use that to calculate the concentration of the original strong acid or strong alkali which that has come from. Okay, so let's have a look here first of all how we do this. Okay, so the theory behind strong acids and strong alkali, it's important that you have a certain amount of understanding about that. So if I take any strong acid, and I just represent it as HA, H for the hydrogen ion and A for the negative ion. The important thing that we know about any strong acid is, and you've been taught this since GCSE, okay, is that it will 100% ionize. In other words, if I have in my strong acid solution 100 moles of HA, therefore I will have 100 moles of hydrogen ions in my resulting dissociated solution and 100 moles of A minus. Likewise, if I have my strong acid at a concentration to begin with of 0.1 mole per em cubed, 0.1 molarity, well, my hydrogen ions and, less importantly, my negative ion will be in a concentration of the same. So this is what we use in order to work out the pH of a strong acid. So you have a formula that you have to know, really important formula. pH is equal to negative the log of the concentration of the hydrogen ions. So when we're trying to work out the pH of any acid, this is the value here that I have somehow got to get to. So for an acid, for example, like if I just took simple monoprotic acid, which is an acid which gives up one proton per mole of the acid, okay, I would say, let's say the concentration of the hydrochloric acid is 0.2 molarity, the concentration of the hydrogen ions are 0.2 molarity, the pH of that solution would be minus the log of the hydrogen ion concentration, which is of course 0.2, and therefore the pH of your solution is 0.6, 0.7, okay? So you have a pH there, 0.7, and that's kind of what you'd expect. You expect a low pH because you have a strong acid in here. So that's pretty straightforward, simple stuff, okay? Now, what if we change the goalposts very slightly? Okay, so we'll just remind ourselves of that equation. And if at any time, if you just want to pause this video and do these, I'll write some problems up. We're not going to do very many because these really aren't very difficult. Okay, certainly take a note of this formula here, minus log of the hydrogen ion. Square brackets, of course, means concentration. Okay, what if I had then, let's say something like, I'll just do a couple of really nice simple ones where you can just check them, just to calculate the pH of, let's say, 0.1 molar nitric acid. Okay, so again that is a monoprotic acid. Okay, so those of you who are mathematically on the ball will realise the pH there is 1.0. Okay, if I had a pH of, let's say, hydrochloric acid, 0.5 molar HCl, so gives me 0.3. Okay, so you should be able to do those, they're pretty easy. Okay, let's take a, move on a wee bit and let's take a diprotic acid. So in other words, an acid which produces 2 protons per mole of acid molecules, and that would be sulfuric acid, would be a strong acid which you would recognize. Okay, so this again, it's not very difficult, but just something you need to consider when you're doing it. So if I this time have my sulfuric acid given to me by the examiner as, let's say, 0.3 molarity, because I produce 2 moles of hydrogen ions per 1 mole of the acid, the concentration, because it's in the same solution, is going to be 0.6 this time. So I need to just bear that in mind when I'm doing my pH calculation, because it then becomes, of course, minus the log of the 0.6. It's not the 0.2 0.3, which some people might accidentally do. It gives you a pH of 0.22222. Alright? So those are all very simple. If I did phosphoric acid, let's say phosphoric acid is a strong acid. Okay, it's not really, but I know for the purposes of this. Okay. So again, we'll just give you a concentration of that. Let's say it's 0.4. You can do the calculation there. Okay, well it's a 3 to 1, so that's going to be 1.2 molarity. So that's going to be minus the log of the 1.2, yeah. And that's going to be negative 0.08. So pH here is negative 0.08. And that's actually quite a good example because it shows that you can get negative pH values. Okay, so don't be startled in an examination if you do indeed get a negative pH value. That's perfectly fine. Okay, so second thing we said that we were going to do then, if we go back to here, is we said we were going to not only calculate the pH, but use the pH to go back and calculate the concentration. Now for this, I'm going to need to unlog my pH, if you like, and get that back to hydrogen ion concentration. So we said earlier, of course, that hydrogen ion concentration, when I minus the log of the hydrogen ion concentration, that give me the pH. So how do I get back to my hydrogen ion concentration? Well, I unlog that pH, okay, or I do 10 to the minus. pH is what you do in your calculator. That gives me the hydrogen ion concentration. So if I took a simple monoprotic acid, for example, hydrochloric acid, and I said to you it had a pH of 1.2, and I'm asking you to calculate the concentration of the acid, not the concentration of the hydrogen ions. So that becomes, I just unlog that, so that's minus 10 to the minus 1.2, gives me 0.063, okay, that gives me 0.063 molarity. Now remember, that's the concentration of the hydrogen ions, but in this instance, because they are the same, they're in a 1-to-1 ratio, that is also the answer to my question, because it's the concentration of the HCl also. Okay, so again, I'll stick a couple of these on the board, and you can have a go at them, and just check that you're fine. Okay, so we'll take nitric acid. We want to calculate the concentration of the nitric acid. It has a pH of 0.75. So I go hydrogen ion concentration equals 10 to the minus 0.75. Okay, just do this. Okay, gives me 0.178. Okay, equals 0.178 molarity, and because it's monoprotic, that is indeed the concentration of the hydrogen ions, which is equal to the concentration of the acid itself. Okay, last one then. Let's say I have HCl has a pH of 2.0. Okay, so I would again got to calculate the concentration of the acid, so we 10 to the minus 2, okay, which gives me 0.01. Okay, because it's monoproduct, that's the concentration of the hydrogen ions, which is equal to the concentration of the hydrochloric acid. So there you go, that is indeed your answer in that case. Right, how do we deal with this then, however, if we get a diprotic acid? So let's take a sulfuric acid this time, okay? Not difficult, but it's just something we need to be aware of. So sulfuric acid, we know, gives us 2 H plus ions, we talked about this a few minutes ago, per 1 mole, so it's a diprotic acid. So let's say this time we have a pH of 1.4. My hydrogen ion concentration then will equal 10 to the minus 1.4. Okay, which is 0.04. Okay, I'll round that up a little bit. Okay, now that, remember, is the concentration of the hydrogen ions. But if we go back to here, every mole of the sulfuric acid gives us 2 moles of hydrogen ions. So the concentration of the acid will be half of the concentration of the hydrogen ions. So the concentration of the sulfuric acid then, okay, will of course be 0.04 over 2. So this time it's 0.02 moles per dm cubed is the concentration of the sulfuric acid. So you've got to bear that in mind. I'll put another one of those up there and you can have a go at it yourself and just check that you. So we'll do H2SO4. We're looking to get its concentration. I'm going to say it has a pH of 0.04. Okay, so 10 to the minus 0.04 is the first thing that we do. Okay, gives me 1.0. Give me 1.1 actually. Okay, 0.1. Okay, we take that and we divide that by 2 because we're going back in the same way as we had earlier. So your answer should be 0.55 is the concentration of the acid. Okay, so that should cover you for being able to work with strong acids, working forwards and backwards. So calculating pH from concentration of acid, calculating concentration of acid from the pH. Now we said at the start of the video that we would look also at doing the same thing with our strong alkalis. So that's what we're going to do. Now, so strong alkalis are obviously a little bit different, and we have got to bring into play here an additional formula, which is called the ionic product of water. Now, I don't want to go into this in too much detail, but the ionic product of water, okay, when I have water, it will ionize very, very slightly to give me some hydrogen ions and some hydroxide ions. Okay, and the ionic product of water is written as the concentration of the hydrogen ions on the concentration of the hydroxide ions at 298 kelvins, which is probably what you're going to get it at in your question. If not, they'll give you the new constant, equals 1 times 10 to the minus 14. Okay, units aren't particularly important, but we'll put them in anyway. So that is a key value here, and this ionic product of water, you have to know the expression here, and you have to know the number as well. Okay, at 298 Kelvin. This value changes with temperature. Okay, but if they give it to you at a different temperature, they'll have to give you the value for the new ionic product of water. Okay, so let's see how we use this to work out pH of strong alkali. So let's do, so the same principle applies for strong alkalis as did strong acids, in that they 100% ionize. So so okay, so if this was 0.1 molarity, my hydroxide ions would be 0.1. I'm not doing, the sodium ions would be the same, but they're not of any relevance. So how do I use this then to work out the pH? Because remember, we said earlier, pH equals minus the log of the H plus ions. So how on earth do I get H plus ions from that? Well, that comes from rearranging the Kw, or the ionic product of water expression. Because if I rearrange that, I can make H plus, my subject, equals Kw over the concentration of the hydroxide ions. Now you might be saying, well, hold on, where the heck are these H plus ions coming from in an alkali? Well, there are hydrogen ions in there. There just happen to be an awful lot more hydroxide ions. So because the product of the hydroxide ions and the hydrogen ions is 1 times 10 to the minus 14, we can use that to work out how many hydrogen ions are in it. Obviously it's going to be a very small number, okay, but nonetheless we use it to get this pH. So my calculation this time becomes 1 times 10 to the minus 14, the Kw, divided by the hydroxide ion concentration, which I take because I know it's a strong alkali, divided by 0.1. So 1 times 10 to the minus 14 divided by 0.1 gives me a value of 1 times 10 to the minus 13, of course. Okay, and that's my hydrogen ion concentration. So I just go back to what we were doing earlier where we minus the log of that. Okay, and that gives me a pH of this instance of 13, which is reasonable. That's what you would expect. You've got a strong alkali here. If I got an answer sort of below 11 or even below 12 probably here, I'd be kind of going back and maybe having another go at this. Okay, so I'll give you a couple to do, and you can have a go at them. Just check that you have, of course, got them right. Okay, so let's do NaOH 0.25 molarity, calculate its pH. Let's do KOH, which has a molarity of 0.005 molarity. Okay, so if you pause the video there, and go and check those. I'll pop the answers up to them now. So the first one has a pH of 13.4, and the second one has got a pH of 11.7. Okay, so all you were doing there was 1 times 10 to the minus 14 over the 0.25, and then you would minus the log of the answer to that to give you that, and here the kW 1 times 10 to the minus 14 over the 0.005 minus the log of that would give you 11.7. Okay, so those should be, I hope, pretty straightforward. Let's go and have a look now at an alkali this time. Okay. So let's take, in this instance, let's take barium hydroxide. Now, what's the only difference here? Well, just like my diprotic acids, my sulfuric acid, my barium hydroxide gives me 2 hydroxide ions per mole of barium. So it's not exactly complex. We'll do Kw over here again just to remind us of the ionic product of water. And we'll do our pH equals minus the log of those H plus ions as well, just again to remind us, and reminder that our ionic product of water is 1 times 10 to the minus 14 also. Now, right, so let's say we have a value here of 0.25 molarity as the concentration of the barium hydroxide that we get. We've got to remember that the ratio here is 1 up to 2, so the hydroxide ions themselves would have a concentration like so. And because of that, my hydrogen ion concentration is equal to, again, the ionic product of water constant divided by the 0.5. So 1 to the minus 14 divided by 0.5 is that. So that gives me 2 times 10 to the minus 14. Remember, that's my hydrogen ion concentration, and to turn that into pH, I simply minus the log of that, okay, which gives me 13.7. And again, that's in and around where I would expect my answer to be. So if I give you one here, let's say I give you another one similar to this. So just to give you barium hydroxide, we'll change the concentration of it. So this time we are 0.1 molarity. If you could go and check or do the pH of that and pause the video. So the pH of that comes out at 13.3. Okay, pretty straightforward, I think. If that too bad, shouldn't cause you too many deaths. Right, so that's fine. We also then have to be able to go back from the pH, like we did with the acid, the pH back to the original concentration of the alkali. So the same sort of principle applies as it did for doing this with acids. Depends where it's monoprotic or diprotic the acid. So let's take a nice simple one to begin with. We've got sodium hydroxide. We've been told it has a pH of 12.8, and we've got to calculate the concentration of that NaOH. So we just have to remember that the NaOH produces hydroxide ions in a 1-to-1 ratio. So I do the same as I did earlier. I 10 to the minus 12.8. Okay. And that gives me 1.58 10 to the minus 13. So that is 1.58 times 10 to the minus 13. Remind ourselves that that gives us H plus ion concentration. We want to find out the sodium hydroxide concentration, but to do that we've got to get the hydroxide ion concentration. So rearranging our Kw expression from up here to make hydroxide ions this time, our subject, hydroxide ions equal Kw 1 times 10 to the minus 14 over the concentration of the hydrogen ions, which we've just worked out, which is 1.58 times 10 to the minus 13. Okay, so 1 times 10 to the minus 14 divided by that gives me 0.063. Okay, 0.063. That, remember, is the concentration of the hydroxide ions, but the hydroxide ions and the sodium hydroxide are the same because they're in that 1-to-1 ratio that we talked about earlier. Therefore, that is my answer to hydroxide ions and to the concentration of the sodium hydroxide. So nice and simple, really. Okay, so if I give you do one here. So if I said you had let's say potassium hydroxide, and that potassium hydroxide has a pH of 13.2, if you could calculate the concentration of that potassium hydroxide, please. Okay, so it comes out there at 0.001 or 0.00099, depending on how much rounding you did. Alright? Okay. Oh, no, it doesn't actually, sorry. I'm reading the wrong one, ignore me. Get rid of that. It comes out at 0.158 in fact, or 0.16, again depending on your rounding there. Okay, I'll give you, let's see, so what about then if we have got alkali like our barium hydroxide that we talked about above. So let's say we have got barium hydroxide, which this time has got a pH of 12 exactly. Now, what do we need to be careful of here? Well, we need to be careful of the fact, in the same way we had our diprotic acids, we get 2 hydroxide ions per mole of the barium hydroxide. So once again, we want to take 10 to the minus 12, because when I take 10 to the minus 12, that gives me my my pH, or sorry, my hydrogen ion concentration, excuse me. Okay, which comes out at 1 times 10, sorry, to the minus 12. Okay, remember I rearranged my Kw expression from above. Okay, Kw 1 times 10 to the minus 14 over the hydrogen ion concentration to the minus 12. That gives me my hydroxide ion concentration, which comes out, in this case, 0.01. Okay, so if I remember that that is the concentration of hydroxide ions, and then if I also bear in mind that the hydroxide ion concentration will be double the concentration of the barium hydroxide itself. So therefore, to get the barium hydroxide concentration, I need to take that value and divide it by 2, which makes it a concentration of 0.005. Okay, so again, I want to put a similar one to this on the board here, and you can, of course, have a go at it. Okay, so let's take some strontium hydroxide this time. Okay, so my strontium hydroxide has got a pH of 11.3, and I would like you to take that and to get the concentration of the strontium hydroxide. Okay, so just pause the video and go and have a go at it. It shouldn't take you very long, I wouldn't think. Okay, so pH, the concentration of the strontium hydroxide in this instance comes out at 0.001 moles per decimeter cubed. Okay, I think, and sometimes if you don't round up proper, or you round up slightly differently, I should say, comes out at that. So either of those answers would indeed be fine. Okay, so just to finish off, I'll just put a few up here, guys, for you, and you can have a go at them again. Pause the video and just check your answers against mine. Okay, so these are just a few checkpoint questions here. So we'll do, first of all, we want the pH of these two solutions that I'm about to do. So we have 0.1 molar sodium hydroxide, and we have 0.01 molar calcium hydroxide. Okay, so if you pause the video there, do those, and then come back to it, and you will see I'll put the answers up to them. Okay, so those are the ones that you should have got. Okay, let's do then, this time we're looking to calculate the concentration of these solutions. So we have KOH with a pH of 14.3, and we have another solution of barium hydroxide, has a pH of 11.0. Okay, so I want you to pause the video, go away and calculate the concentration of those two solutions. So this one is 2.0 moles per decimeter cubed, and this one is 5 times 10 to the minus 4, or 0.0005 moles per decimeter cubed. Okay, hopefully that sorts that out. There's plenty of examples in your notes. If you aren't getting these right from the one that I've done on the board, please go back over the video or come and see us. Thank you.